This video introduces multiple linear regression modeling. This is the first of two parts. In this video we'll take a look at building and evaluating a linear regression model, and a second video will cover using the linear regression model for estimation and prediction. Now, we are already familiar with simple linear regression, where our model is y is equal to b0, the intercept, plus b1 x1. Multiple regression is going to add additional factors to this model. For instance, a second factor would have its own slope, b2 times x2, and we could continue adding additional factors as necessary. And as we move from simple to multiple linear regression, we move from fitting a line to the data to a plane and then a hyperplane. However, the parameter estimates are done in the same manner, minimizing the sum of square errors, and that's something that we allow our software to do for us. For this video, we're going to continue using the home sales. We've already built that model, modeling the price of a home in thousands of dollars by square feet, but now we're going to take a look at a couple of additional factors that we might have recorded. We'll take a look at whether bedrooms adds additional information, as well as whether the condition of the house adds additional information. And when we talk about adding additional information, what we're looking at doing is explaining more of the variability in the selling price of the house, seeing if we can come up with a model that does a better job of predicting the price of the house. Now, the model that we found under simple linear regression is price is equal to 2.7 plus 0.047 times square feet. If both of these additional factors go into the model, the new model will be b0 plus b1 times square feet plus b2 times bedrooms plus b3 times condition. Now, one thing to keep in mind is these parameter estimates we found under simple linear regression are going to change when we add additional factors. Every time we make a change to the model, all parameter estimates are going to change, and along with that, the significance of the parameters might change as well. As we go through building the model, we'll use the same 5 steps that we used for simple linear regression with a couple of changes. We'll plot the data and evaluate it, but now we're going to look at something called a multivariate correlation plot. Hypothesize the model, estimate the parameters. When we go to evaluate the model and the parameters, we're going to spend more time focusing on the parameter estimates themselves. Simple linear regression, there's no difference between the t-test for the parameter and f-test for the whole model. But under multiple regression, there will be a difference. And then using the model for estimation and prediction is very similar. As in simple linear regression, with step 1, we'll look for 3 different things. First, when we take a look at the distribution of the individual variables, we'll be looking for the range of the variables so that we know where we can use the model. We'll also look for outliers, identifying observations that should or potentially should not be in the data set. Third, we'll look for relationships between variables. However, the key difference in multiple linear regression is we have a lot of variables to look for relationships between. We do this in a scatter plot matrix, which is a collection of scatter graphs. The scatter plot matrix is laid out in a table that gives us the opportunity to compare price by square feet, price by bedrooms, and price by condition. And when we do this, we see that we have strong positive correlations between price and square feet as well as price and bedrooms. And there is a negative correlation with price and condition. Good thing is that all of these relationships appear to be linear. We can also look for relationships between different factors. For instance, we have a very strong correlation between square feet and bedrooms. As the number of bedrooms goes up, well, the square feet of the house has to go up to hold the bedrooms. So we would expect a relationship there. Question is, are these two factors giving us the same information about price? Right above the scatter plot matrix, we have a multivariate correlation table, and this gives us the actual correlation coefficients between the different variables. We see that we have strong correlations with price, square feet, and bedrooms. and a not so strong, not quite a strong correlation between price and condition. The strongest correlation in this table is between square feet and bedrooms, 0.96 correlation. These ones represent correlations between variables in themselves. So we consider those to be trivial correlations, and we don't worry about those. In step 2, we hypothesize a model. And we'll start by building a model that has all the factors in it, and we'll go ahead and use that. We won't bounce back and forth between different models in this particular video, but under the step 2, the null hypothesis is that y is equal to y bar, and in that situation all of our parameter estimates are going to be 0. Alternate hypothesis, if this model is correct model, at least one of the parameters will be significant. And this is the hypothesis we're going to test in step 4. In step 3, we go about estimating the model parameters. As we set the model up, we'll identify price as the y variable, square feet, bedroom, and conditions of the house as model effects or factors, and when we're satisfied, when we've got all the factors in the model, we'll click on the Run Model button, and that will generate several different reports. The first report that we'll take a look at is the parameter estimates, where we find the actual values for these parameters. This is typically the third or fourth table down in a regression report. And from the first 2 columns, we see that the model is y, or price, is equal to 28.51 plus 0.0359 times square feet plus 1.694 times the number of bedrooms minus 7.616 times the condition of the house. And this can be interpreted as each square foot is worth 0.036 or $36 because price is in thousands of dollars. Each bedroom is worth $1,694. Each condition point is worth a loss of $7,616. And the starting point for the model is $28,510, which you might think about that as the price of a typical lot with no house upon it. Now these interpretations, another thing to keep in mind is that these interpretations assume that all other factors are held constant. In step 4, we're going to run 3 different checks. Number 1, we'll check the whole model fit. Number 2, we'll check individual parameters to see whether they're significant. And third, we'll check the form of the model to see if a linear model is correct and whether we've captured all of the information in the data. Under the whole model F test, we'll evaluate that in the analysis of variance table. And what we're again checking here is that null hypothesis from step 2, that none of the factors in the model are significant. And if that's the case, all of the parameter estimates are going to be 0. The F ratio compares the mean square model with the mean squared error. It forms a ratio of the two. And the ratio that we have here is 1434 divided by 14, which gives us an F ratio of 97.0395. The probability of a more extreme F ratio, if there's no relationship between any factor and the response, is less than 0.0001. So we know from this that at least one factor in the model is significant. Next, we take a look at individual parameters within the model. And here we're going to check the T ratios in the parameter estimates table. We're only going to take a look at the factors in the model. We're not worried about the intercept. That can be significant, not significant. It doesn't really matter to us. As we work our way down, the T ratio for square feet is 3.29, which means that this parameter estimate, 0.0359, is 3.29 standard errors away from 0. So this is a significant factor. The second factor, 1.69 for bedrooms, is only 0.39 standard errors away from zero. The probability of observing something more extreme than 1.69, if that null hypothesis is true, in other words, if the true value of bedrooms is 0, is 0.7. 70% chance of a more extreme estimate if the null hypothesis is true. So this factor is not significant in the model. We would want to take that out of the model. The third factor, condition, is highly significant. It's 5.4 standard deviations from the mean. So we'd like to keep that in the model. Now at this point, ordinarily what we would do is we would go back to the model specification page, remove bedrooms from the model, and run a new model with square feet and condition only. We're not going to do that. We're going to press on so that we can take a look at the rest of the model building in a single video. The final thing that we have to do under step 4 is check to see whether the form of the model is correct. And along with that, we're also checking to see if our model is picking up all of the information in the data. Are we including all of the factors that we need to include in the model? If that's the case, then the residuals are simply going to represent random noise. If we see patterns in the residual, that means that there's an additional factor that should be included, or potentially that we've got a nonlinear relationship that we need to adjust. What is a residual? Well, a residual is the difference between the observed value of y and the predicted value of y. For example, the first home that we've got in our data set was 720 square feet, a 2-bedroom, condition 3. The price that we've recorded for that home is $38,000. However, the model predicts $34,930. So the residual for that home is the difference, $3,070. And as we take a look at these residuals, we're calculating the residual for every observation in the data set. And then we are plotting the residuals predicted by residual. When we take a look at these residuals, we're going to check 4 regression assumptions. We want to see whether those residuals are independent, if they're normally distributed, if the expected value is 0, and if the variance is constant. If we satisfy all 4 of those assumptions, that means that the residuals are pure random noise. And that means that we do have the model that we're looking for. Taking a look at these residuals, we don't see any patterns between the points. It looks completely random as we move along, so we can assume that we've got independence. We don't see any regions where all of our residuals are above or below the horizontal line above 0. So second assumption, expected value is 0. Looks like it's met. Variance looks like it is fairly constant here. We don't see any patterns of increasing or decreasing variance. So it looks like we have constant variance. When we save our residuals and plot the distribution of the residuals, we can check normality. We don't have a normal distribution showing on here, but we do have our normal quantile plot. And when we take a look at the residuals along that normal quantile plot, it looks like they're all nicely aligned on that red diagonal. So that helps reinforce the idea that our residuals are normally distributed. If we take a look at the goodness of fit test and keep in mind that the null hypothesis is that the residuals are normally distributed, we see that our p-value is very large. And we know that we don't reject the null hypothesis when we have a large p-value. So the goodness of fit test supports the idea that these residuals are normally distributed. Now, given this, we could move along and use this model for estimation and prediction. We'll do that in a separate video. However, just keep in mind that at this point we would actually be going back to step 2, hypothesizing a new model without bedrooms.